Perception is the identification and interpretation of sensory information in order to understand the presented information. Our brain takes in information through the senses and attempts to understand through context clues and/or connecting to things we already know. An illusion is a distortion of the senses resulting in a distortion of reality, which can reveal how the human brain normally organizes and interprets sensory stimulation. Out of all of our senses, humans rely most upon their sense of vision. So we're going to use our sense of vision today and see how our brain perceives different things that we're looking at. Our brain is stimulated by new information or situations. Things that are familiar receive less attention. With this cartoon image of an elephant, your brain, after seeing so many pictures of regular elephants, sees this as new and interesting, and it starts to pay more attention to this than it had been the other elephant pictures before. Once again, we're seeing a change. Our image is now in black and white, which is different than all the color images we had been looking at. Now, upon first looking at this, it appears that this is just another black and white image of an elephant. So our brain may not pay that much attention to it since we've already seen a bunch of pictures of black and white elephants. However, this is an impossible object. Because we live in a three-dimensional world, our brains try to interpret two-dimensional drawings as three-dimensional. With an impossible object, looking at different parts of the object makes one reassess the three-dimensional nature of the object, which confuses the mind. So here are some other examples of impossible objects. Different contexts can distort our perception. Line A and line B are exactly the same length. They appear to be different because of the angles that are surrounding the lines. Line A appears longer because of the outer-facing angles, whereas line B appears shorter because of the inward-facing angles. Center circles are exactly the same size. On the left, the center circle appears larger because it's being surrounded by small objects. On the right, the center circle appears smaller because it's surrounded by larger objects. Both tables are the same length. The table on the left appears longer because it's narrower, but lengthwise they're the same. The height of the hat, the distance from A to B, is the same as the width of the hat, the distance from C to D. The colors from the image on the left and the image on the right are exactly the same. The image on the left with the outlines, it makes the colors appear darker, where in the image on the right without the outlines, the colors seem more vibrant and brighter. In the top picture, the red squares are all the same color. The bottom picture, the green squares, are all the same color. The differences between the right side and the left side have to do with the color that the square is on, as well as the color that surrounds the square on the sides. Colors appear to be shifting. However, that is just an illusion based on the changing lines. For this image, imagine we have a light source coming from the bottom, and this makes it look like we have indentations, and so we'll call those dimples. On this image, we will assume that the light source is coming from the top, and so it appears that we have these protrusions coming off of the surface, and we'll call those pimples. Watch the image on the left, as all it does is twist. As the image rotated, we now have pimples instead of dimples. Watch the same thing happen to the image on the right. Simply rotating the image gives us a completely different perception of the image, and that has to do with how we perceive shading. Because we live in a three-dimensional world, when we see shadows, that tells us something about what we're looking at. And so based on the shading and the shadowing in these pictures, we assume that we either have protruding or we have sunken in parts of the object. Our brains may perceive the same thing differently. And when we do this, we also should try to see if we can flip the way we're perceiving the image and see it the other way as well. So one way of looking at this object is a three-dimensional cube where the white area that's kind of in the center is protruding out towards you. Another way to look at this is a three-dimensional room where that same white area is now the back corner of the room, where we have a floor and we have two walls. So for each of these next images, see if you can see them in both ways. Is the circle inside the box or outside of the box? Which way are the stairs going? Is the door opening towards you or away from you? Is the cat going up the stairs or down the stairs? What word do you see? Do you see optical or do you see illusion? Do you see teach or do you see learn? Do you see good or do you see evil? Do you see victory or do you see defeat? Do you see alive or do you see dead? Do you see me or you? No matter what way this word is, it says the same thing: ambiguity. Do you see 6 vases or 12 faces? Do you see a duck or a rabbit? Do you see the head of a donkey or the entire body of a seal? Do you see a silhouette of a face or do you see the body of a saxophonist? Do you see the old woman or the young girl? Do you see a front view of this face or a side profile pic of this face? Do you see a skull or a lady looking at her reflection? Do you see a balding man looking towards the left? It's his side view, and he's holding on to the chest of his jacket with his hand. Or do you see a couple under an archway with a dog laying in the street? Do you see an old couple staring at each other? Or do you see two men that are sitting? And you also can see a very large vase in the center of the picture. Looking at this picture, you should see Albert Einstein, a very famous physicist. You now should see a picture of Marilyn Monroe, a famous actress. And now you once again should see Albert Einstein. What way are these dots moving? Are they moving up and down? Or are they moving from side to side? As you switch your focus from the yellow circle to the red circle and back, it appears as if the circles on the outside change directions. Which way is this woman spinning? Is she spinning to the right or is she spinning to the left? You'll also see this in some of your notes this unit. For example, these three skulls, which way are they spinning? Certain patterns may result in the perception of movement when there actually is none. So the next few images that we'll be looking at are still pictures that appear to have movement. And a lot of times this movement has to do with where there's shading in the picture. On this one, where the white lines intersect, it appears there's a gray splotch. And as you look around the picture, it may look like they're even blinking. But remember, this is just a still picture with nothing moving. One thing that our brain tends to do is follow the direction of arrows or things that look like arrows. And since this image has arrows that are converging together, it appears that these gears are slowly spinning up next to each other. Here's another example of arrows that give the perception of movement when there actually is none. It appears as if the outer ring is shifting up and down. However, there's no movement in that outer ring. What is happening is that it is simply changing colors from white to black to white to black. And that change in color gives the perception of movement when no movement is there. This is another example of how changing color can appear to produce motion. It looks like these little stick figures are riding an escalator and then jumping off, but nothing's actually moving. The background is changing color, but the boxes really are not spinning. This image is moving, and many people say that it is moving side to side diagonally, kind of like it's ping-ponging off of the sides. Actually, it is simply moving up and down in a straight line. The changing colors on the image make it appear like it might be moving in other directions. So there is movement on this screen, but it's not the circular rotation that you think. Instead, each turtle is actually moving back and forth in a completely straight line. So you can see the example of this in the black circle on the right. And if you pick any of the turtles from the circle and you follow that single turtle, you'll see that that turtle is only moving back and forth on its own straight line. Here's the same thing, but with more complex patterns. But still, every turtle is only moving back and forth. Stare at that red dot in the center. It's fine to blink, but don't shift your gaze. Keep looking at the red dot. I will be changing or adding an image to the screen on the right. Once I add the new image to the right, shift and look at the center of the picture on the right. It may appear that that new picture on the right is moving in some way. It's actually almost an identical picture to what you had been staring at on the left, but it's a little blurry and offset just slightly. And so when you shift your gaze from the left image to the right image, your brain thinks they're the same and is trying to overlap them, but since there's a slight difference, it appears that there's movement when there's none. This is moving. Stare at the center of the spiral. It's fine to blink. Just don't shift your eyes around. When I switch to a different picture, notice what's happening in the picture. Although this is a still picture, there appears to be some movement because your eyes had become so accustomed to the spinning spiral. We'll try that one more time. So once again, stare at the center. And then when I switch to a new image, look to see what happens in that image. This is a famous painting called Starry Night by Vincent van Gogh. And notice the swirly patterns, especially in the sky. Because you were looking at the spiral, when you look to this, it makes it appear that those swirling patterns are actually moving. We can perceive spatial relationships incorrectly. All of the horizontal lines on this picture are completely parallel. They may look like they're at angles due to the colored boxes being offset from each other. Same with this picture. All of the horizontal lines are parallel. All of the red lines are parallel and perpendicular to each other. Because they're overlaid on circles, it may appear as if those lines are wavy when they are actually straight. Once again, these lines are all parallel. The differing cross hatches makes them appear to be at different angles. All parallel and perpendicular. Parallel and perpendicular. Because the rectangles in that circle in the center are going a different direction, it makes that circle appear to be more three-dimensional on a two-dimensional picture. Pareidolia is the tendency to see faces in inanimate objects or abstract images. Studies show that the brain favors faces over other patterns, as well as being hypersensitive to stimuli it sees on a regular basis, as well as anything it could perceive as a threat. This is believed to have an evolutionary connection because faces could either tell us things that will help in our survival or potentially harm us in terms of survival. So here are some examples. Although the brain is good at identifying faces, it sometimes perceives them incorrectly. This is called the Thatcher effect. It occurs when a picture is turned upside down, but the mouth and eyes are kept the right way up. The brain is often unable to see that anything strange has happened when the picture was turned the wrong way up. The reason this is called the Thatcher effect is because the researcher who presented this information had first done this with a picture of Margaret Thatcher. When the Thatcher illusion was first developed in 1980, it presented a huge challenge to the way that scientists understood how the human brain processes faces. It showed that people don't just think about the face as a whole, but rather understand each of its component parts and assemble them into a whole. So the two pictures that are on the left show the Thatcher effect, and the two pictures on the right are just showing the normal picture. Here are some other examples. Our brain often fills in what it perceives as missing information. You may think that you see a white triangle on top of an outline of a red triangle and 3 circles. However, there's no white triangle. The only thing on this picture are 3 red angles and 3 incomplete circles. Your brain is filling in what it thinks is missing. This is the law of closure, and it states that individuals perceive objects as being whole when they are not complete. When parts of a whole picture are missing, our perception fills in the visual gap. So while this may appear to be the outline of a 3-dimensional box, it's only a collection of circles with different white lines running through them. At first glance, this one may be difficult to figure out, but once we animate it, you can tell that it's a Dalmatian. So here we have just a bunch of random shapes, no particular pattern. If we arrange them in a certain way, now here we have what appears to be a triangle. And if we arrange them again, we can see the image of a panda. What is the word on each slide? Once trained, our brains work very efficiently at the task it has learned. There is an error in the words inside the triangle. Many people often have difficulty finding the error because their brain overlooks it. If you look closely, the word "the" is twice. When you read, you are actually reading as a whole, and especially if there are mistakes or errors, sometimes your brain will just skip over those, especially like a repeated word. For this one, do not read the words, but instead say the color in which the word is printed and see how fast you can do that. This task is more difficult than people think, since we have conditioned our brains to read. When we tell our brains to ignore the words and instead look at the color, that's a very difficult task for our brains to switch to. And so it can make a task like this very difficult. See if you're able to read this paragraph. The phenomenal power of the human mind. According to a research at Cambridge University, it doesn't matter in what order the letters in a word are. The only important thing is that the first and last letter be in the right place. The rest can be a total mess, and you can still read it without problem. This is because the human mind does not read every letter by itself, but the word as a whole. Sensory adaptation is when our brain ignores an unchanging stimulus. This is an important aspect of how our brain functions because our brain is continually being bombarded with sensory information. And if we paid attention to every single piece of information, that would create an overload on our system. And so what our brain really focuses on is new and different pieces of information. So for this, stare at the black dot in the center of the screen. Try to keep blinking to a minimum and don't shift your eyes around. What you should start to notice out of your peripheral vision is that the splotches of color should start to disappear. And that's because you're telling your brain to focus on that black dot, and it starts to ignore the other information around it. An afterimage is an image that continues to appear in one's vision after the exposure to the original image has ceased. Positive afterimages appear the same color, while negative afterimages appear as the contrast. So stare at the dot in the center of the screen. And when the colors change to gray, you should see a faint residual color. All of those gray rectangles are actually the same shade of gray, but since you're seeing some residual colors, you're seeing after images of the colors that were present. Stare at the cross in the center, and you should see a green dot that is going around and around the circle. Now, if you try to find that green dot, it now suddenly seems to disappear. There actually is no green dot. When you're staring at the center cross, what's happening is that pink dots are disappearing, and you're seeing an after image and you're seeing the contrasting green even though there's really no color there. And so when you try to locate that green by going around the circle, that's why you can't find it, because it really doesn't exist. The green you saw was a perception from your brain. Here's the same thing, but with these blue dots, you should see an orange after image. And another example, with these orange dots, you should see a faint blue after image. For this, you'll want to stare at the dot in the center of the screen, and you want to try not to blink. Blink if you need to, but try not to. So now, stare at the dot. Once that image changes away from this color, you should see the pyramid and the surrounding in actual color. That's actually a black and white image, but you see the after image, which causes it to appear like it's in color. Let's try another. Same thing. Look at the dot in the center. We'll do this one more time. And one more after image, look at the white cross in the center. When I switch the screen to all white, you should see a red, white, and blue flag very faintly on the white screen. Magic eye images. A magic eye image starts with a grayscale image, then a two-dimensional pattern to camouflage that image is developed. Finally, a computer program using an algorithm takes the image and the pattern and orients repeating patterns to the intended depth of the hidden image. When someone looks at a magic eye, the repeating pattern feeds the brain the depth information encoded into it, and the brain perceives the hidden picture. If you've either never looked at a magic eye image or had difficulty trying to find the magic eye image in the past, it helps to hold the center of the image right up to your nose. Focus as though you are looking through the image into the distance, and then very slowly move the image away from your face. Once you perceive the hidden image in depth, you can look around the entire 3D image. The longer you look, the clearer the illusion becomes, and the farther away you hold the page, the deeper it becomes. So here's the first one. This is what you should have been able to see. Here's the second one. Here's what you should have seen. Third. There's the actual image. Fourth one. And one more. So the last thing are that illusions are often used in advertising. So for each of the following images, there are illusions within the image that is being shown. See if you can identify and find them.